Hello, should we start?
Yes, sir.
Yes, sir.
Okay. Vishal sir, should we start?
Yes, sir. We can continue now.
Okay. So can you see my screen?
Yes.
Yes, okay. Okay, so we will have the just small recap of the yesterday's lecture. Then we will go for the homework which I have given. Hope you all have solved that homework and able to design the converter, buck converter. If not, today we will just have the one solution which I have solved, and then we will go for the next converters. Okay, so yesterday, first converter which we were talking, the DC-DC converter which we were talking is the step-down converter. It is also called as the buck converter. So the overall arrangement of the buck converter is a input voltage, output voltage will be getting across the this one. So as the name suggests, it is a step-down means the output voltage is equal to or the lower than the input voltage. So that is the buck converter or the step down converter, and it has the one switch semiconductor. Here the semiconductor switch can be the MOSFET, IGBT or anything, but for simplicity we have shown as a idle switch which can turn on and off once you will give the gate pulse. So that is the switch, and then the diode, inductor and capacitor. So this is the overall arrangement for the buck converter. Operation point of view, yesterday we saw whenever this switch is getting closed, so this source is getting connected to the output, connected to the output load through the this inductor, and current will flow in this direction. So this is the path where the current will start flowing when switch is closed. So that time the voltage across the diode is opposite. So it is in reverse bias and the diode will not conduct. As the current is flowing through the inductor, inductor current will start increasing for whenever there is a switch is on. And once the switch is off, when you open the switch, so that time what will happen? So this source is getting separated from the this remaining circuitry, and that time whatever the inductor voltage is there, so that will getting applied across the diode and it will come forward bias, and the current will start the free wheel through the diode. So the current direction is in this, but already the load is there, so it will oppose the inductor current, and inductor current will start the reducing. Similarly, in next cycle, again when switch is closed, again start the increasing and decreasing. So this is the inductor current. Whenever switch is closed, the voltage across this inductor will be whatever. If you apply the Kirchhoff's voltage law for the this range, this circuit, then it will be the voltage across this inductor will be this voltage minus the output voltage. And whenever there is a switch is open, so this is the path, and if we apply the KVL here again, so the voltage across the inductor will be the minus VO. So this is the overall basic operation of the buck converter. From that basic operation, we just tried to have the derivation. So that is the when switch is closed, so we will saying the VL is equal to VS minus VO, which is nothing but again L di by DIL by dt. If I simplify DIL by dt by taking L on this direction and integrate it on the both the side by taking this dt on this side. So if I integrate it, so I will get the delta IL when closed, which is equal to Vs minus Vo by L into dt. D is nothing but dt, which is varying between the 0 to 1, and t can be written as the t on time divided by the total time, and the t is the total time of the one cycle, and 1 upon t 1 upon t is equal to 1 upon f, which is the frequency. F is the frequency. Similarly, when switch is open, So that time the equivalent circuit is this one, and the voltage across inductor is minus VO. So which is nothing but again L DIL by dt. Again, if I simplify, DIL by dt is equal to minus VO by L. If I take dt on this side and integrate it on both sides, so delta IL open I will get as a minus VO by L into 1 minus d into t. So I asked to just try these equations in the home. So hope you have all have tried, and if you have any doubt, so you can ask. So if I now have the, if we see here, whatever closed delta IL and the open delta IL, if we add both this, it should be zero because there is no difference in the this. It is a periodic we are taking. So this, if I make it a zero, and by keeping the equation, if I solve, so I will get the, this is the equation for the output voltage. So VO is equals to VS into D. So D, as I said, D is varying between the 0 to 1. So when D is equal to 0, VO is equal to 0. So output voltage is 0. And D is equal to 1, then VO is equal to VS. So the voltage, output voltage varies between the 0 to VS. VS is nothing but the input voltage. So it is always less than the input voltage or equals to the input voltage. So that's why it is a buck converter, and this equation we can use for the getting the output voltage from the this converter. So that's all. We derived some other equation like a I max value, then the I mean value, then we calculated the L minimum which is required for the continuous current, continuous conduction current. Then we calculated the inductor value in terms of the delta IL. Then we calculated the value of the C in terms of the ripple ratio of the output voltage. Okay, from that we solved one equation where we calculated the duty, output voltage from the duty and the I max, I mean, and the ripple ratio. This was the homework which I have given to you uh, to solve the or the design the buck converter. So anyone tried for this one? Anyone? Or till the buck converter, whatever I have taught in that, you have anyone has the any doubt, anything clarification is required?
Yes, sir. Try. I have tried to solve it.
Okay, good. So did you get any results for this?
Yes, sir. For the current, I have applied V naught by R. I got the maximum output current at 1.8 amperes.
Okay, correct.
Then for the
That is the average current you got,
duties,
1.8 ampere.
yes, sir.
Whatever current you are saying, that is the average current,
Yes,
IL.
average
IL
current.
is equal to
And
IO is equal
for
to,
the
yeah,
for the duty cycle, I have got 0.375 duty cycle.
correct.
Then the choosing the frequency, I have chosen 100 kilohertz frequency, switching frequency for that.
Okay, okay.
From then the inductor selection for the inductor, I have got 208 micro Henry value of the inductor.
208. This is the L minimum you are saying, or the
Yes, sir.
L minimum? It is higher. Maybe you did some mistake actually. For the 100 kilohertz, at least it should not be that much value.
Sir, actually it's 20 point.
So
For 100, you are getting the 20.
20.8,
Okay,
20.8.
8 microhenry.
And for a continuous conduction, it's getting 31.25 microhenry.
How much
And
higher you have taken value?
1.8. 0.5 times.
Okay, 1.5 times. Okay.
And for the output capacitor, it's 7.5 microfarad.
Okay. Okay. Good. Good. Okay. So for remaining peoples, I will just show the one solution which I have misderived. So we will go through the solution, and at least from once after this solution or the today after this lecture, at least try with the different values. So like he said he used the 100 kilohertz. So you can use the different switching frequency and try to solve the this thing. Okay. So this was we were talking. So the equation, the design problem was design a buck converter to produce a output voltage of 18 volt across the 10 ohm resistance. The output voltage ripple should not exceed the 0.5%, and DC supply voltage is 48 volt. So that was given, and design the continuous inductor current, specify the duty ratio, switching frequency, the values of inductor and capacitor, peak voltage rating of each devices, and RMS current of the inductor and capacitor. So for that, what is given? VO is given, VO is 18 volt, VS is 48 volt, and R is given as a 10 ohm. Okay. Also a given as a ratio of the required output voltage ripple ratio, that is delta VO by VO, which is equal to 0.5%. So this is the one value is given. So this much data is given. So we know the D duty. So this is the direct equation we have, which is the VO is equal to D into VS. So D is equal to VO by VS. If I put these values, 18 divided by 48, you will get the 0.375. Now I have assumed the 50 kilohertz. You can assume different value as well, no issue. So one switching frequency we will assume, and from that we can calculate the other values. So for 50 kilohertz, if I calculate the L minimum, it is coming around the 62.5 microhenry. We have the L minimum equation, which is 1 minus D into R divided by 2F. So if I put all this value, I will get the 62.5 microhenry. Now average current inductor, which is equal to IL, which is equal to IO, and which is nothing but the VO by R. So which we can directly calculate as a 18 by 10, which is equal to 1.8 ampere. Now delta IL, again delta IL, we have the equation as a VS minus VO by L into dt. Now we have the all these values. So if I put these values, 48 minus 18, 62.5, this I have taken as a L minimum.
Hello? So you are not audible.
Oh, sorry, someone has muted me. Maybe muted all, and that I got muted. Now can you hear me?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. If you won't get the voice, just clarify me. Okay. So where I was when I was explaining. So
Previous
here
slide.
my sound was audible for this one, for
Yes,
this
sir.
part.
Yes, sir.
Okay.
Yes, sir.
Okay. So here we calculated the delta IL, which is equal to 3.6. Here we have not increased the inductance. Whatever L minimum value we got, that only I have used here. And with that, delta IL is 3.6. So from that delta IL and IL value, I can calculate the I max and I min. I max is nothing but IL plus delta IL by 2, which is equal to 1.8, and delta IL is 3.6. So 3.6 divided by 2 is again 1.8, which is giving the 3.6 ampere as a max value. Mean value is nothing but IL in minus delta IL by 2, which is equal to 1.8, and 1.1 equals to 0. So what does it means? So the current is going from 0 to 3.6 and again coming to the 0. So this is the waveform we are getting if we use the minima. So this point is 3.6, 3.6 Imax, and this is the 0. Okay, but as per the condition, we require to uh, have the continuous conduction, not critical conduction also. So this is the critical conduction with a L minimum value. So if we want to continuous conduction, the L minimum has to be increased to a some higher value. So what I did, I have taken the 1.2 times of the L minimum as a L. So if I do that one, so my L value is 78.13 microhenry. So if I put this value, so of course I have considered the 1.25. So delta IL will be reducing by the 1.25. So the same thing I have here. So delta IL previous whatever I am getting 3.6 divided by 1.25, if I do, it will comes as a 2.88 ampere. Now with this value, if I calculate the I max, it is 1.8 plus 1.44, which is nothing but 3.24 ampere. I mean is equal to 1.8 minus 1.44, which is equal to 0.36 ampere. And this is the greater than the 0. So it is not touching to the 0. So now your current is going from the 0.36 to the 3.24, which is the continuous conduction. So with this inductance value, we are fulfilling the criteria of the continuous conduction. So that's why we can take the inductance value this and have the this one. Now inductance RMS, actually this is a simple derivation for the inductor RMS. We have the this what we can say the waveform of the inductor. From that waveform, you can calculate the RMS value. So the RMS is nothing but the square root of the area under curve. So if we apply the area under curve and take the square root of that one, you will get the RMS value. I will not go into the derivation of this. I am directly giving the equation. So which is nothing but the IL square plus delta IL by 2 by root 3 whole square and square root of this. So this is the equation you will get for the ILRMS. So it is a simple mathematics, nothing special for this one. So you can take the area under curve and square of that, and then square root of the whole square. So you will get the RMS value, which is the formula for the any RMS calculation of the any RMS value. So if we apply that one, you will get the this equation. And if I put the my values in this, which is IL is 1.8, delta IL by 2 is 1.44, root 3 whole square. If I calculate this, it will give us the 1.98. So the inductor RMS current is 1.98 ampere. Similarly, for the capacitor value we can calculate by this formula 1 minus T divided by 8L delta VO by VO uh, into F square. So if I put the value 1 minus 0.37375, then the 8 into L value is 78.13 microhenry. This value is given as a 0.5%. Okay, but we cannot put the percentage value. So 0.5%, which is nothing but equal to 0.005. So if I put this value and F is 50 kilohertz. So if I put all this value, I will get the capacitance equals to the 80 microfarad. Similarly, from the graph of the capacitor current, if you calculate the RMS value, you will get the delta IL by 2 into root 3. This is the equation. So if I put these values again, I will get the 0.83 as a RMS value of the capacitor. Now, if we check in any case, so if I go back here, you can see what is happening when this switch is open. So the voltage across this, if you switch consider, this switch is consider. So if I apply the KVL here again, so what is the maximum voltage applied here, which is equals to the Vs. So this voltage is getting applied across this switch. Similarly, when switch was closed, so that time if I apply the again KVL here, so this is the voltage here, which is nothing but the again Vs. So if you see the voltages across the diodes and the switch, is maximum voltage is getting applied as a Vs. Here if you apply KVL, so which is nothing but the this VL minus VO, and VL is nothing but Vs minus VO. Again, if we apply this VO, so you will get the one will becomes plus and minus, and we will get the Vs only across this one. So the maximum voltage across the diode and the switch is always the Vs for the buck. So maximum voltage applied will be for the our problem will be the 48 volt. So from this, if we want to choose the switch, it should be the higher than the 48 volt, right? So this is the overall solution for this one, for this problem. Do you have any?
I had a doubt.
Yeah, please.
Sir, for continuous conduction mode, is there any range to assume values for frequency? Because all the other parameters are dependent on that one value.
Actually, how is it? So it will depends on the miss. We will decide means whether we will go for the higher switching frequency or the lower switching frequency. And again, we will have whether we are going to use the IGBT or we are going to use the MOSFET, or what is the voltage range, because each will device have the different criteria. If I consider the thyristor, so thyristor will operate with a very low frequency, like a 50 hertz, 100 hertz on that, up to maximum a 400 hertz. But if we go for the IGBT, IGBTs can operate up to the 20-25 kilohertz. Okay, but if I want to use the MOSFET, then I can go for the any switching frequency. So that time, uh, so in that case, we will go for the higher than the 25, 30, 50. So that will depends on the whole on the our design criteria. So there is no such thumb rule that we can go for this one and this one. Only thing is that as you increase the frequency, your filter will get reduces. So that also you have seen. As you increase the F, L minimum requirement will get reduces. So L reduces, C reduces, so your filter requirements are getting reduced as you go for the higher switching frequency. But as you go for the higher switching frequency, you will increase the switching losses and conduction losses. Not conduction losses will remain same, but the switching losses will increase, because that much time we are switching on and switching off the switch. So when you consider the any switch, there will be the two types of the losses. One is the switching losses and one is the conduction losses. Switching losses is the losses when we are turning on and turning off the switch. So at that time, there is some losses are happening, that is called as the switching loss. And whenever there is a continuous current is flowing through the switch, so it is called as the conduction loss. So these are the two main losses in the switches. So as you increase the switching frequency, more and more switching losses will increase. So that much heat will be generated, and that has to be taken from the switch. Otherwise, switch will blast. So that much, what we can say, the cooling system is required. Extra cooling system is required for the switch. So on all that basis of that, we can choose the switching frequency, then the which type of the switch we are going to use. So all these things will be considered, and from that the range will be decided. One more aspect is that if you go for the higher and higher switching frequency, there is a one phenomena is called as the EMI EMC, electromagnetic conduction and electromagnetic emission. So these are the again the filters required for the any converter. So that will the requirement of this filter again increases as the switching frequency increases. So there is a trade-off between the switching frequency and the your filter size and the switch which you are using. Because again, if you want to go for the higher switching frequency, the switch cost increases. So all that kind of things considering some range is considered for the switching frequency, and from that all the values will be calculated, and from that we can have the final design. Got the points?
Yes, sir.
Yeah. So all these things are practical things. Once you start the practical design, then you will come to know all that kind of things. But of course, here as a theory point of view, we can consider any frequency now. But you can see that as the frequency increases, the your L requirement reduces, and you will have the smaller and smaller smaller and smaller your converter. Just one example. Now, if you see the chargers, so previously the chargers were the 10 watt or the mobile charger I am talking, 10 watt or the 20 watt, that also were the bulky. But now the chargers are coming to the 120 watt, and that they are almost same size of that whatever they were of the 10 watt or the 20 watt. So how they have achieved this? So this is achieved by the increasing the switching frequency. So higher switching frequency, the all inductor and capacitors will get reduces, and you will get the smaller size of the that one. But for that again now people are moving to the GAN devices. GAN is the device which can operate to a very high frequency, almost 500 kilohertz, 1 megahertz. So in that range, the now converters are operated this one to getting the chargers. Okay. I hope this will clarify your doubt.
Sir,
Yes.
which circuit is used in EV bicycle charging?
EV vehicle charging, you are saying?
Yeah, yeah,
Hello?
yeah.
Yeah, actually, in electrical vehicle charging system, there are again two types of the charging systems. One is there which will be the onboard. I'm talking about the car and all that kind. Two wheelers and three wheelers are different part. For the cars and everything, they have the onboard or the on the car itself. There is a one charger will be there, which is called as the onboard charger. And also you must have seen the some like a petrol pump. There are some chargers are installed on the many places, and we can charge the car from the that charger as well. So that is also there. Okay. So where the onboard charger is there, which has the lower capacity, means it will be ranging from the 2 watt to up to a 20 watt, 20 kilowatt, sorry, 2 kilowatt to 20 kilowatt. So in that range, we have the onboard charges for the different manufacturer, and that charging will take the single phase AC and charge the battery. So how it will works? So this will be having the first whatever AC is there, so that will be converted to the DC by using the some controlled rectifiers. So that will convert to the DC, and there will be the DC-DC converter to charge the battery. Again, there is a basic requirement that whatever your supply input supply is there and the battery is there, so in between there is a requirement of the isolation, galvanic isolation. So in that case, all the whatever converters are used, that they are isolated converters. So whatever the buck converters and boost converter, now we are talking, these are the non-isolated converter. But this type of the converters will not directly used in the our EV application. So there we will have the isolated converters. I will just, if time permits, I will go just show you the how the isolated converters are there and which are the different types of the isolated converters are used for the PV application, EV application. Sorry. Okay. So just I will not
Yeah.
explain all the converters, but I will give the overview what are the converters are used for the EV application.
Yes, sir, sure.
So once you will get the idea, you can go through the nowadays the internet is a big thing where you will get all the data. Only you needs a willingness to get that data actually. So I will give the overview. You can go through the internet videos and you will get the more details for that one. Because that much time we
Okay,
don't
sir.
have. I can also give all the details, but we don't have that much time.
Yes, sir, sure.
Yeah. Okay. Then moving to the next converter, which is the boost converter. It is also called as the step-up converter. So boost means boosting or the stepping up voltage. So the name itself implies that this output of this converter is either equals to the input voltage or the greater than the input voltage. How much greater we can get? So that we will come to know from the equation how much we will get. And but theoretically we should get the infinite output voltage for the from the by varying the duty. So that is the criteria for the boost converter. Now arrangement point of view, you can see this is the boost converter. So here the voltage source, again the output voltage source is there, output voltage is there. Only change is that the inductor, previously it was here for the buck converter, now it shifted to the this position. Then diode is shifted from this to this position. Okay, diode is shifted from this position, and the switch is shifted from this position to this position. So this round shifting has done. So switch come from here to here, then diode went from here to here, and again inductor came from here to here. So that is the change in terms of the boost converter. But with this change, you can see the very much change in the we can say operation point of view. So what is the change that we will see? Just I will erase this so that I can explain the working of this one again. Okay, now same thing again when switch is closed and switch is open, that are the two cases. But with this, what is happening, you can see when this switch is closed. So previously switch was here, now switch is here, and if we close the switch, what is happening? So this is the voltage source, this is the inductor, and here you are shorting. So the source is getting short through the inductor, and always the current will follow the low impedance path. So if this path, if you see, it has the high impedance. So the current will try to flow this one. So and the voltage across this inductor is applied as a Vs. So what will happen with the inductor current? As we have given the voltage applied across this one, your inductor current will start increasing here. Okay. So for the switch is closed, so the current follows this path and the inductor current will rise. Now when switch is open, what is happening? Now there is no path to flow the current. So this voltage and this voltage will get applied across the diode, and diode will comes in the forward bias, and whole voltage, the current will flow in this direction. So but what is happening? This and these two voltages are getting applied across this resistor, and this resistor is opposing the whatever current flowing. So you will get the reduction in the current. So again, at this instant, we will switch on this switch, and the rising of the current will happen. Then again, the falling of the current. So in that way, again, here also you are getting the similar inductor current, which we are getting with the previous case, but the paths are different. The path is when switch is closed, you are getting this path, and when switch is open, you are getting this path. Okay, and the voltages across the inductors are also different in this case. when switch is closed, the voltage across this inductor is this voltage is getting applied. Whereas the when switch is open, the voltage is this voltage minus this voltage. Sorry, VO minus VS you are getting across the VL. So that are the different voltages you are getting. Okay. So the same thing we will apply, and the similar method we will try to have to the derive the equation, output voltage equation. So when switch is closed, so this is the closed position, diode is getting reverse bias, and the current is flowing in this direction. So the voltage across this is getting applied as a Vs. So you can see this voltage is getting applied, and the current is flowing from in the increasing direction. So VL is equal to Vs is getting applied. Simple Kirchhoff's voltage law, and inductor voltage is nothing but the L dIL by dt. So if I simplify this equation, dIL by dt is equal to L. If I take on this side, it will give us as a Vs by L. Now, if I make the rate of change of current is a constant, so the current increases linearly if we consider. So we can say that dIL is nothing but the delta IL, and dt is nothing but the delta t. So basic mathematical assumptions I am applying here. And if I take the dt on this side and if I integrate it or the integrate here itself, so you will
Screen
get
is not
sorry.
screen is not visible.
Uh, okay, just a minute. Oh, sorry. Now,
Yes.
so where I was when the screen was not appearing. Actually,
Yes, sir.
someone has tried to share the screen. That's why my screen got disconnected or something like that happened. So try to avoid that such things so that there will not be interruption in the things. Okay. Sorry. So these things was visible, right?
Yes, sir.
Okay. Okay. So the same which I explained. So here when switch is closed, so this is the closed path the current is taking, and the voltage across the inductor is VL by Vs. So if I apply VL is equal to Vs, which is nothing but the L dIL by dt. So dIL by dt is nothing but Vs by L. So if I take the dt in this direction and integrate on the both side, so I can say the change in the current when switch is closed, which is nothing but the delta L close, and integration of the Vs into dt, Vs by L. Vs by L is constant, and integration of dt. So the integration of dt is this one, which is nothing but the dt, which is integration is t over the period of dt to 0. So I can say integration from 0 to dt into t. Sorry, into dt. So if I integrate this, so it is giving the t, and if I put this value, so it will give the dt. So delta IL closed is Vs dt into L. So this is the equation we are getting when switch is closed. Now when switch is open, so this will get open here and this will get closed here. So that time you can see the voltage across this inductor is minus or the Vs by VO. So and as the voltage is getting reverse direction, it will try to pull down the current in this direction. So the same thing we will apply here. So you can see here the switch is open, so the this path is open, and the diode is forward bias and it is getting shorted, and the inductor voltage is nothing but Vs minus VO. So which is equal to VL is equal to Vs minus VO and nothing but L di by dt. Same thing we will do dIL by dt by taking the L on this direction, integrating it, and integration will be here from dt to total T, because this is the off time, which is the dt to T. So if I put that value and all solve it, I will get the Vs minus Vo into 1 minus d into T by L is the delta IL open. Okay, again same thing, delta IL close. So this is the delta IL close and delta IL open. So if I add both this, it should be the 0. So there is no change in the inductor after the time of one cycle. So this is the T. So after T, you are reaching to the initial position, which was the I minimum value. So the same position you are reaching after the T. So that things we can apply. Delta IL close plus delta IL open equals to the 0. Now if I put the values, Vs delta IL close what Vs into dt by L plus delta IL open, which is equal to Vs minus Vo into 1 minus d into T divided by L, which is equal to 0. Now this L will get cancelled, then this T will get cancelled. And if I simplify this, Vs, Vsd and Vsd plus this 1 minus d terms is there. If I take the Vs multiplication outside, so this is the Vsd plus 1 minus d minus Vo into 1 minus d. Simple simplification. Okay. Then d here it again getting cancelled. If I take this term on this side and if I take this out, then you will get the Vo is equal to Vs divided by 1 minus t. So this is the output voltage equation for the boost converter. So the same thing we are applying. So whatever the delta IL we are calculating when the switch is closed. So whatever voltage across the inductor is applied, from that we will calculate the delta IL close. Similarly, when switch is open, we will see the voltage across the inductor, and from that again we will calculate the delta IL open. We will add the both the delta IL close and open and equal to 0 because they are reaching to the same position. So there is no change, delta IL, no change after the T cycle. And if I put all this value and simplify, I will get the output equation. Clear? Now, again, D will remain the same, which is varies between the 0 to 1. So if I put value of the D equals to 0, so this will becomes the 0. 1 minus 0 is 1. So Vs by 1. So output voltage is equal to Vs when D is equal to 0. Okay. Now when D is equal to 1, D is equal to 1, 1 minus 1 is 0. Vs by 0, you will get the infinite. So ideally, you should get the infinite output voltage by varying the D. But in practical, it is not possible. We will try to cover that part also. Practically, by varying only D, you will not get the infinite output. Why? So that we will come in some of the derivation. Actually, I will show you the derivation where it will show that you will not get the infinite value as the D varies. But this is the ideal case. So in ideal case, when D is equal to 0, you will get the input voltage. And when D is equal to 1, you will get the infinite voltage. So this is the ideal case considered. And for the other values, say if I take the D is equal to 0.5, so in this case, what will be the VO? So VO is equal to Vs by 1 minus 0.5, which is nothing but the 0.5, or we can say 2 times of the Vs. So by if D is equal to 0.5, you will get the double of the output voltage than the input voltage, 2 times of the Vs. Similarly, for the different values, you will get the different values of the VO. So you are starting from the input voltage and as D increases, you are going for the higher and higher output voltage. So the output voltage is varying between the input voltage to the infinite, or the input voltage to the higher than the input voltage. So that's why we can say this is the boost converter. Here you are getting the always output voltage which is greater than the input voltage. The same equation we can derive by this equation, but this you can take it as a homework. So these things also we can apply. VL is equal to VSD when switch is open, and VS minus VO into 1 minus D when switch is closed. Sorry, here switch is closed and switch is open, which again we can say it is equal to 0, and we can derive the equation from this as well. Okay, so the same thing here I have explained. VO is equal to VS minus 1 minus D, and the equation shows that if the switch is always open means D is equal to 0, which is equal to D is equal to 0. The output voltage is same as the input voltage, and as the duty ratio increases, the denominator becomes smaller and resulting in the larger output voltage. At the duty ratio of the switch approaches 1, the output voltage goes to the infinity according to the above equation. However, equation is based on the ideal component, as I said. So you will not get in any of the case, you will not get the infinite voltage from the, if we consider the non-idle switches or the non-idle components. So real components that have the losses will prevent the such as occurrence, as shown later in this section. So I will show in the later section that this will not possible with the non-idle component. Clear? Boost converter.
Yes, sir.
Okay.
Yes, sir.
Some of the other equations we can derive simply by considering the input power is equal to output power equation. So output power is nothing but PO is equal to either VO into IO. VO is the output voltage, IO is the output current, or we can say the VO square divided by R. So these are the basic electrical equations, output power. So VO square by R, or the VO into IO. Now we have considered the assumption that whatever input power is there, so the same we will getting supplied to the output. So there is no losses in the converter. Whatever input power is there, so the same will be applied to the output power. So the input power, which is nothing but is Vs into Is. And if we consider here, so you can see Is will be here, right? So this is the Is. So this will be the Is. Now when switch is closed, so the Is is flowing in this direction, and when switch is open, the Is is flowing in this direction. So you can see the Is is same as the IL. So there is no difference between the Is and IL. So the same thing I have written here. VSIS equals to the VSIL is the input power. Now, as I said, the non-lossy converter, whatever input power is there, VSIL should be equals to the output power. So the VSIL is equal to VO square by R. Now VO equation just now we have derived. VO is nothing but Vs divided by 1 minus D. So if we put that value here, you will get the VSIL as Vs square divided by 1 minus D square. 1 uh, uh, if I take the okay, Vs divided by 1 minus D square, Vs square into D square. This R should be not here, actually here. Now 1 Vs if I cancel here, so this VL is getting cancelled. IL you will get the Vs divided by 1 minus D square into R. Correct? Same equation you can write in terms of the output voltage as VO square by R divided by into Vs. So this is the one equation, because Vs into 1 minus Vs square divided by Vs if I take here, and Vs divided by 1 minus D is nothing but the VO, and here square you can say the VO square Vs into R. So this equation you can write. Similarly, VO square by R. So this is VO square by R is nothing but VO IO. So if I replace this VO square by R by the VO IO, I will get the Vs. So just in different terms. Why we are writing different terms? Because sometimes we have the input voltage and the R value. So that time we can use this equation to calculate the IL. Sometimes we have the output voltage, input voltage and R value. That time we can use this equation to calculate the IL. Sometimes there is only output voltage, output current is given and input voltage is given. R is not given. So in that case, you can use this equation. So simple thing. But of course, if we use the VO and IO, then from that you can calculate the R and you can use this equation as well. So it is just a mathematical manipulation. So just write down this equation again. VO is equal to Vs minus 1 minus D. Vs divided by 1 minus D. Then write down the other equations, like directly you can write the IL equation. IL is nothing but the Vs divided by 1 minus D square into R, VO square by Vs by R, VO IO divided by Vs. If you remember the derivation, all that kind of things, there is no need to remember all this equation as well. So you can just go every time converter only you have to remember and try to solve at that time and derive the equations. So instead of remembering all this equation, you can just remember the operation of the converter. So operation of the converter, and then how we are calculating the delta IL and all these things. So if we try to do this and the basic things if we use, so everything you can able to derive actually. Okay, so now we have the IL value as well as the delta IL we have calculated. So this delta IL open and close, both delta IL we have calculated, delta IL close Vs dt by L, and delta IL open Vs minus VO 1 minus dt by L. So from that we can calculate the I max and I mean. I max is nothing but uh, IL plus delta IL by 2. IL in first equation we calculated at Vs 1 minus D square by R plus delta IL by 2. Here you can use the delta IL open or the delta IL close. So here it is used as a delta IL close, which is nothing but Vs dt by L. So delta IL by 2 is nothing but Vs dt by 2L. So this is the I max equation. I mean equation, IL minus delta IL by 2. Why do we are taking delta IL by 2 and minus delta IL by 2? Because whenever we have this inductor current, so this is the inductor current. So this is the I max. I max. I will shift to so that I can write clearly. Okay, so this is the your inductor current. This is the IL, and this you are getting as a I max, and this is the I mean. You are able to see my screen, right? Different screen, not presentation.
Yes, sir.
Yeah, okay. So this is the I max and I mean, and whatever IL we are saying, that is the average current, which is nothing but here. So this is the IL. Okay, and this value we are saying as a delta IL. This is the delta IL. Okay, so total delta IL from here to here, this IL average value. So if we want to have the average of this triangular, so what it will be the, so this will be the, this area, or this will be the delta IL by 2, and again here also you will get the delta IL by 2. So I max if I want, so this value plus this value, which is nothing but IL plus delta IL by 2. Similarly, for the I mean, this value minus this value, so IL minus delta IL by 2, you will get the I minimum. So same thing I have done. So I max is IL plus delta IL by 2, and I mean is IL minus delta IL by 2, which is by putting values of this, you can get the IL max and min. This equation also you can write down. You have seen that whatever buck converter we have derived, for the same thing I am applying for the boost converter. So the similar way I am applying for the boost converter as well to get the different equations. So similarly, we can apply for the other converters as well. Only we needs to have the operation understanding, and then we can derive all this equation. Okay. Then again, whatever we did for the calculating the L minimum. So L minimum, when it will be the L minimum, that is the critical conduction, means the current is just reaching to the 0. So if your L value is less than this value, so this current will go down, more down, and you will get the this type of the current. So at this you will get the discontinuous conduction, and this is the case when it is just reaching to the 0 is the critical conduction, and from that you will get the L minimum. So above that L minimum, you will get the continuous conduction like this. Below that, you will get the discontinuous conduction, and at L minimum, you will get the critical conduction. So how you will get? So here you can see the waveform again. If I draw for the L minimum, so the L minimum means your I minimum value is reaching to the 0. So if I equate the I minimum value equals to 0, so we can say Vs minus 1 by d square R minus Vs dt by 2L equals to 0. So if we simplify this equation, if I take this term on this side and rearrange, so I can say Vs divided by 1 minus d square R equals to Vs dt divided by 2L, which is equal to, again, 1 Vs is getting cancelled here, and we can say if we simplify this one, and t is taken as a down here, f t is as a written as a 1 upon f. So this you can write. Then LFF term is taken outside. So LFF minimum, you will get the d into 1 minus d square r divided by 2. Also, if we want to do the L minimum value, F only we have to shift on this side. So you'll get the equation as the L minimum as a D into 1 minus D square R divided by 2F. Write down this equation again. Again, design perspective, it is useful to express the inductance value in terms of delta IL. Sometimes the people ask the inductors in terms of the delta L. They give the requirement of delta L, say 1% of the output current, or in that way. So in that time, we can say L is equal to Vs dt into delta L, which is nothing but the Vsd into delta L by F. So this is the derived from the delta L equation. Delta L equation was the for the when switch is closed. So whatever delta L was, Vs dt by L was there. So L is taken on this side and delta L in this side, and only T is taken as a 1 upon F. So this equation you can write. Clear? Now we have the 5 minutes break. Then we will continue for the step up, voltage ripple of the capacitor. Okay, so sharp 5 minutes. It's now 8:07. Sorry. Then we will meet at the 8:12. I'm not asking to anyone directly. I am taking as a break, but please try to come at sharp at the 8:12. Okay. I have given one extra minute. It's already 8:13, and I hope everyone is again joined back. So considering that and not wasting everyone's time, I will start. Okay. Uh, so we just derived the what is the output voltage and how the inductor currents are going, what is the Imax, I mean, and the average IL current, that things we have derived. Now there is a one more component called as the capacitor. Why we require the capacitor here? Now you can see uh, this load or the output we are considering as a DC. So the voltage has to be DC, and that is also the constant voltage, and the current has to be DC, and which should be the constant, which is required as a say IO current is required to me, and that has to be constant. But operation point of view, what is happening when the switch suppose this capacitor is not there, okay, then what is happening when switch is closed, so that time current is flowing in this direction. So there is no current flowing from the this diode or the, so this IO is equal to becoming zero if this capacitor is not there. And when switch is open, that time of course this current is flowing. Okay. So what is happening? So the diode current, if we see, so when switch is closed, so there is no current flowing in this diode, and when switch is open, so that time the whatever the current is there, so that will be flowing through the diode, and the same can go to the IO. But this type of the current we don't want at the output. We want a output as a IO only. So I want a IO this one. So I required this IO. So how you will get this IO? So that will be supplied by the having the one capacitor here. So this we will have. So if I have the capacitor here, so which can charge or discharge. Now I have the capacitor in the circuit, so which will charge and discharge. So what is happening when the switch is closed and there is no current in the diode? So this is the condition. So that time whatever current requirement is there, so that will be supplied by the capacitor. So capacitor will supply the capacitor start the discharging, and it will supply the current to the load or the load or the output. So you can see the capacitor current. So this is the what this IO is nothing but the output voltage divided by resistance, which is equal to VO by R. So this much current will be supplied by the capacitor. So the capacitor current is minus VO by R when switch is closed. Now when switch is open, that time what is happening? The source and inductors are supplying the current, but the total current will not be given to the output. In that case, what is happening? Some current will flow to charge the capacitor, and remaining current will flow, which is equal to IO. So this much current only we require to flow through the load. So this IO will be there, and this total diode current minus IO. So whatever current coming from here, which is flowing through the diode, minus IO. So this part will be used to the charge the capacitor. Okay. So here discharging the capacitor and here charging the capacitor. And as it is the storage, so whatever charge and discharge are there, so that will be equal. So after this time, it should be the at the same voltage or the charging position after the total time t. Okay, so that is the phenomena we are considering, and the same thing uh, from the same this graph, we can say what will be the our capacitance value. We can calculate. How we will calculate? So from this graph, you can see. So this is the charge current, and this is the discharge. Charge of the capacitor and discharge of the capacitor. Charge of the capacitor is the delta Q, which is nothing but this is a area under curve we have to take. So area of the rectangle area is nothing but length into width. So length or the width, we can say it is a VO by R, and the width is not, this is the VO by R, and this is the dt. So if we multiply, this will give the area under curve, and this delta Q is nothing but the C into delta VO. So these are the equations we have seen. So delta VO, we can say VO dt R by C by taking the C in this side. So you will get this equation. Now T is nothing but 1 upon F. If I put that value, so I can say the F here. Again, it will be given in terms of the ripple of the output voltage. So I will take this VO on this side. So it will give the delta VO by VO is equals to D divided by RCF. So this is the different than the which we are got for the buck converter. So the filter requirements for the buck and boost are completely different. L also, if you have seen the different equations you will get. Okay. So similarly from this equation, if we want to have the C, you can say D divided by R delta VO by V term taken on this side, you will get this equation. So this is the capacitor equations. Okay, so write down this equation and this equation. With this equation, we will solve uh, one design problem, and then we can move to the next converter. Okay, so this is one part. I don't know. Okay, so I will just explain what is this. Uh, till now, what we have considered, whatever capacitor is there, so that we are considering the ideal capacitor, actually. But in practical, this ideal capacitor will not come as a like a only capacitor. It will have the some series resistance in the capacitor. So every capacitor will have the one series resistance. It is called as the equivalent series inductance or the ESL or the equivalent series. Actually, it has the both inductance and the resistance, equivalent series resistance and equivalent series inductance. But this we can ignore ESL, and only we have to take the equivalent series resistance, which is called as the ESR. So the ESR will be there. And now what is happening? The total ripple, if we consider the ripple across this, so that will be the ripple across the ideal capacitor value as well as the ripple across this. So if we add both this, then only you will get the actual ripple across the capacitor. So we can say delta VO ESR, equivalent series resistance ripple, which is equal to whatever the current flowing through this one and the value of this delta IC into RC will be the ripple across this ESR resistor. So total ripple will be addition of this. So it will be always less than whatever delta VO you are given. So that should be less than the whatever delta VOC plus delta VO ESR. So that is the one non-ideal condition we have to consider when there is a calculation of the delta VO. Similarly, uh, for the inductor, so inductor also we have considered there is no any losses, but in practical inductor has the small resistance, so which will cause some loss. So for the boost converter, we had this equation. Now we previously considered as a PS is equal to PO. So input power is equal to output power. But as the inductor is there and which has some resistance and which has some losses, so there will be some loss across the inductor. So this we can write as a P into RL. So which is nothing but IL square into RL. Okay. So this loss will be there. So input power I have written as a VS into IL, output power as a VO into ID, because the average of the ID is the nothing but the output power, and plus IL into RL. So the RL is the series resistance of the inductor. Now if we consider this, and the diode current will be the ID into, because it is in the op condition, and whatever inductor current is there multiplied by 1 minus D, you will get the diode current. Now substituting all this value, what you will get? Vs into IL, PO IL 1 minus D, IL square RL. Vs is equal to, here the IL is getting cancelled, this IL and this IL is getting cancelled. So Vs is equal to VO into 1 minus D plus IL into RL. So IL is giving ID by 1 minus D. ID is nothing but VO by R, 1 minus D. So substituting for the IL, you will get the Vs is equal to VO RL divided by R 1 minus D plus VO 1 minus D. So if I, from this again, if I take the VO equation, what I will get? Vs divided by 1 minus D into bracket 1 divided by 1 plus RL into bracket R into 1 minus D square. So this is the actual output voltage for the boost converter, considering the non-idle of the inductor. So you can see the previously you are getting the output voltage as this only. Now this term has get added in the output voltage, and which will depends on the your R value, D value and RL value. Okay. So this is the actual equation you will get. And if I plot this equation in terms by changing the D value for the constant D, so what you will get, you can see for the idle case, as I said, this it will start with the Vs value, and it will, as the D reaches to the 1, it reaches to the infinite. But in non-ideal case, if we consider, so it will not reaches to the uh, infinite, but it will reaches to the 0 value actually. So this is the actual waveform or the actual output voltage you are getting for the boost converter for the non-ideal case. So it can see not more than the 4 times output voltage you can achieve from the depending on the R value. Okay, so in non-ideality case, you will have the not the infinite. Hello, hello. Is anyone have the doubt? Okay, so this is the actual non-idle inductor we have considered, and with that we are getting this type of the output voltage, which is not going to the infinite, but it is going to the 0 as the D reaches to the 1. Similarly, if we calculate the efficiency graph, of course there are lot of losses. That's why this graph is happening here. So for idle case we are not considering any loss, so there you will get the efficiency as the 100% efficiency. You will get the constant efficiency graph here. But as the D increases in non-idle case, the efficiency is reducing and it is becoming zero efficiency at the D is equal to D is equal to 1. So that is the overall, we can say the non-ideal case or the how actually boost converter is operating. So in our idle case, we can operate like this, but in non-idle case, it is not possible to get the infinite output because any of the device will not be there in practical. There will not be any device which is idle device. All devices have the some losses, some stray capacitor and inductances, all that kind of things, and that will cause the output of the uh, our devices. Okay, so just to get the idea how the non-ideality affect on the our converter, so I have explained, but we will still assume the ideal consideration and have the one design. So write down this design. Design a boost converter that will have the output voltage of 30 volt from the 12 volt source. So source is lower than the output. So that is the requirement. Design for the continuous inductor current and output ripple voltage of less than 1%. So 1% output voltage ripple is given. The load resistance is given as a 50 ohm. Assume ideal component for this design. So this is the design criteria for the boost converter. Vs is given as a 12 volt. Vs is 12 volt. VO is 30 volt. Then R is 50 ohm, and the ripple ratio of the output voltage is given as a 1%, and idle components. So from this, if we want to design the boost converter, first we can calculate the D. D is nothing but the 1 minus Vs by VO, because VO is equal to actually Vs divided by 1 minus D. So if we want to calculate the D, you can take the this on this side, and if we simplify it, you will get this equation. So 1 minus Vs minus D. So you will get the 1 minus Vs is 12, VO is 30. So this is giving the 0.4. 1 minus 0.4 will give the 0.6. So duty requirement is 0.6. Switching frequency here they have selected as a 25 kilohertz. And then see here they have mentioned that the above the audio range. So because audio range is up to the 20 kilohertz, so below that, above that, some frequency is considered, and then putting the L minimum value, we can calculate D is equal to 1 minus D square R into 2F. We'll get the 96 microhenry. Now we can take the higher than this value to get the continuous conduction. So L is assumed here at a 120 microhenry. Uh, and from that, if we calculate the IL is nothing but Vs divided by 1 minus D square into R. So it is giving the 1.5 ampere. From this IL, we can calculate the I max and I minimum, or first we can calculate the delta IL by 2, which is Vs dt by 2L. So this is the 1.2 ampere for this value of the 120 microhenry value of the inductance. And for that, I max is 2.7, I min is 0.3. So it is above the 0. So it is in continuous conduction. The capacitance formula we can directly use. Here it is given the 1%. 1% is nothing but 0.01. And all this value, if I put, the 48 microfarad is the capacitance requirement. Okay. Then the second this thing, what I will do, I will give that into the chat so that you can have this as a homework. I will put this into the chat. So before going to or going out, I don't know that I have the access to the chat, or I will send it to the sir so that he can forward it to you for the tomorrow's homework, actually, the boost converter design. Okay.
I have saved it, sir.
Okay. Okay.
I have taken screenshot of it and I will share
Oh,
with students.
yeah. Please share so that this can be the homework for the tomorrow.
Yes, sure.
Okay. Then after completing of the buck and boost converter, we'll have the one more basic converter, which is called as the buck boost converter, or it is also called as step up step down converter. Means it can step up the voltage as well as the step down voltage. What is that? So the output voltage can be the lower than the input voltage, also the higher than the input voltage as the D varies. And the structure of that buck boost converter is simply here. So somewhat different changes are there. So you can just analyze how is it there. So the source and the load output voltage will remain at the same position. Now the switch position is same as the buck converter. Okay. The diode and inductor is getting replaced than the buck converter, but the direction of the diode is reversed here. You can see previously for the boost converter, the direction was in this direction. Okay. Now the direction of the boost converter is changed here. So we can say in buck boost converter, the position of the buck converter for the switch is taken, and the position of the diode from the boost converter is taken, but a reverse direction. And inductor position is same as the again to the here it is taken as a for this one here. Okay, so this is the overall structure for the buck boost converter. Again, how it is operating. So similarly, when switch is closed, the current will start flowing through this. Just a minute. When switch is closed, so the current will flow through the this, and it will start the increase the current through the inductor. Now when switch is open, what is happening? The switch is open and the current, this is the current, so the current has to flow somewhere. So in that case, this diode will come in the forward bias and the current will flow in this direction. So there are, you can see the switch is closed, different paths it is taking. So for first path it is going through this one, and for second path it is going to the through this direction, and it is reducing the current. So the same inductor current we are getting, but the because of this arrangement, first when switch is closed, the current is flowing in this direction, and when switch is open, so current is flowing in this direction. Same thing, what we will do when switch is closed and when switch is open, we will apply the voltages across the inductor. What we will get? So when switch is closed, this voltage is getting applied across this one, whereas the when switch is open, so this voltage is getting applied across this. Okay, so from that we will derive the equations. Okay, when switch is closed, so this is closed, so this one diode is reverse bias, current is flowing in this direction. Now this voltage, input voltage is getting applied across the inductor. So VL is equal to VS. So VL is equal to VS, and VL is nothing but L DIL by dt. So again DIL by dt is equal to VS by L. So similar thing, if I take the dt in this side and integrate it on the both side with 0 to dt, same thing I am doing, only whatever inductor voltage is there, so that I am taking. So I will get the delta IL close is equal to VS by L into the dt. Okay. So this equation I got when the switch is closed. Now when switch is open, as I said, the current will flow in this direction. So VL will be equals to the VO. So here the it is VS is not getting applied, the VO is getting applied. So VL is VO, and again it is nothing but the LDIL by dt. So DIL by dt is equal to VO by L. Again integration and calculating the delta IL, you will get the VO 1 minus dt into L. So same shown here, when the switch is closed, rising, switch is open, falling, and the voltages applied across the inductors are, this is the VS and this is the VO. Again, we will apply delta IL close plus delta IL open is equal to 0. So what is delta IL close was there? VS dt by L and VO 1 minus d into t by L, which is equal to 0. So if I simplify this equation, what I will get? T will get cancelled, L will get cancelled, and if I take this term on this side and 1 minus d on this side, you will get the VO is equal to minus VS into d by 1 minus d. So one thing you can observe here, you are getting the minus value. Means whatever your polarity you have considered, here plus and here minus. So but actually you are getting the opposite of this voltage. Means if I apply the 10 volt with a polarity of plus here and minus here, so you will whatever output voltage you are getting, so that will be polarity plus on this side and minus on this side. reverse voltage you are getting across the load. Okay, because you already seen that this is the minus. Same. Uh, okay. Now if I put the value from 0 to 1, again if I put the value D is equal to 0, so here it will become the 0 and output voltage is 0. Now if I put the value of 1, this is 1, 1 minus 1 again 0, it is giving the infinite. If I put the 0.5, what is happening? So D is equal to 0.5. Here you are getting the 0.5. 1 minus 0.5 is again 0.5. So 0.5 divided by 0.5 is 1. So you are getting the output voltage is equal to minus Vn, minus Vs. So what we can say, whenever the D is less than 0.5, you are getting the buck operation because the output voltage is less than the input voltage. When D is equal to 0.5, you are getting the output voltage equal to input voltage. And when D is greater than 0.5, you are getting the boost operation or the higher value. Just you can put one value, say 0.7. So if I put here 0.7 divided by 1 minus 0.7 is 0.3. So 0.7 divided by 0.3. So it is a 7 divided by 3 is 2 point something. So 2 point something of Vs you are getting as a output voltage. Okay. So here you can see D, whenever D is less than 0.5, you are getting the buck operation. Whenever D is greater than 0.5, you are getting the boost operation. So it is giving the both the thing, buck operation, which is the step down operation, as well as the boost operation, which is the step up operation. So that's why it is called as the buck boost converter, right? So you can write down this equation: VO is equal to minus Vs D divided by 1 minus D. Again, to calculate the IL, what we will do, we will consider the PO. PO is nothing but VO square by R, and PS is nothing but Vs into Is, and input power is equal to output power. So VO square R by is equal to Vs into Is. So the average source current is related to the average inductor current by Is is equal to Is. How we can say? Uh, if I go for this one, okay. So Is, you can see when there is a switch is closed, so that time whatever Is is there, so that only flowing through the inductor. And when switch is open, the Is is not flowing through the inductor. So if I consider the inductor current, so and multiply only on time, then I can get the Is. So the same thing I have written, Is is equal to whatever inductor current is there. If I multiplied by only on time or by the D, you will get the Is. So if I put this Is value here, you will get the VO square R is equal to Vs IL into D. So IL, if I simplify, you will get the VO square Vs by RD, PO Vs by D. Again, these are the all simplified equations which we are done for the buck as well as the boost converter to calculate the IL. Once you calculate the IL, delta IL we already calculated. So we can calculate the I max and I min by putting the values for the IL and delta IL by 2. So I max is IL plus delta IL by 2, and I min is IL minus delta IL by 2. So this is the equations we are getting for the I max. This is for the I min. For continuous current, again minimum value we will calculate equals to 0 to get the continuous conduction. So if we equate this equation to the 0, you will get the minimum inductor and frequency multiplication as a 1 minus d square r divided by 2. And if we calculate the L minimum value, it will be 1 minus d square r divided by 2f. Clear? Maybe equations how you are getting, you will not be able to understand, but you try to understand the operation of the converter, and from that try to derive all the equation. So once you will try to derive, then only you will come to know how the equations are coming. By just only explaining the equation, you will not understand. But once you start the solving this equation, you will get the all these things. And same thing, if you see the for the all three converters, we have followed the same procedure to calculate all these values, like I max, I mean, delta IL, then the IL, then the L minimum, all that kind of things we did for done for the all these things. So the same thing you have to follow, you will get the results. Again, for the ripple also, output voltage ripple, same thing. If you see, so whenever there is a switch is closed, so no current is flowing from the input to the output. So the whole current will be supplied by the capacitor, which is equal to delta Q. And this we can say is as a say C delta V, and which is again this we know this is the VO by R. This is the VO by R, and this is nothing but the dt. So if we multiply this to get the delta Q, because this is a rectangular and delta Q is the area under curve, we can have the VO by R into length into width, which is VO by R into dt. So if we simplify, you will get the delta VO by VO is equal to d by RCF. So the peak to peak variation in the capacitor current is the same as the maximum inductor current. So the delta VO ISR, we can say delta ICRC, and this delta IC is nothing but the delta, IL max. So the same that max current is flowing through the IC. So we can say if we want to the ripple across the ESR, equivalent series resistance, we'll say the IL max into the RC. Okay. Any doubt regarding the buck boost converter? I went very fast for this one because we have to cover a lot of things still. So that's why I thought to go somewhat higher speed. But we will spend some time to clarify the doubt if you have anything. Anyone? Is everyone understood? You can ask any question for the buck boost. If not, then just I will touch up the next converter, which is called as the Chook converter. Some people call it as a Cook converter, Chook converter. So this converter is by the name of the scientist called as a Chook. So the scientist name itself is given as a for this converter because he only proposed that converter, and that's why the name also given from his name only. I met him also. This scientist I have met. So one of the there was I visited one of the conference. For that conference, he came and he proposed this converter. So from his name only, this converter has derived actually. So again, this Chook converter is also a non-isolated converter. So beauty of this is that so the if you consider the previous all buck converter or the boost converter, what is happening? Just if I draw the, I will share the. Okay, so if I consider the buck converter, so what is happening? So this is your uh, buck converter. Sorry. Uh, yeah, right. Sorry, this is the boost converter I am drawing. Okay, so this is the boost converter, right? And buck converter, if we consider buck converter here, the switch, diode, inductor. Okay, so this is the buck. This is the buck, and this is the boost. Okay, what is happening here? So if you consider the boost converter, so the boost converter, this inductor is present on the input side. Okay, and the for the buck converter, this inductor is present at the output side. So this inductor is filtering for input for the boost, and this inductor is filtering output for the buck. So that was the difference between the buck and boost in terms of the our we can say the filtering. So the Chuk converter, whatever is considered, the can be so here this is also a buck boost converter. Okay, it can be the output can be the either larger or the smaller than the input, and this is the polarity of reversal of the output. So there are 2-3 things I have consider in this converter. So in this converter, so this is the structure. You can see the inductor is present on the input side, inductor is present at the output side. Also, one more thing you will get the for the buck boost, you have seen that the polarity of the output is getting reverse. So in this converter, you will get the same polarity as that of the input voltage, and the inductors are present at the input as well as the output. So that is the thing. Of course, the number of devices are getting higher here. Switch and diodes are same, but the passive components, the inductors are two now, then the capacitors are also two now here. But with that, we will get the filtering at the output as well as the filtering at the input. So it is a good filtered output converter we are getting. So that's why it has the some advantages. Of course, some disadvantages like a more number of devices, but the filtering part and all that kind of thing, you are getting the good filtering at the input as well as the output. Also, there is no change in the polarity. The same thing I have written here. The output voltage magnitude can be either larger or the smaller than the input, and the polarity reversal of the output means there is no reversal of polarity. The inductor on the inputs acts as a filter for the DC supply. So at the input side, it is acting as a filter for the this input supply, prevent large harmonics content, unlike the previous converter topologies where the energy transfer is associated with the inductor energy transfer. For the Chuk converter depends on the capacitor C1. The analysis begin with this assumption. Both inductors are very large. We'll consider both these inductors very large value, and the currents in them are the constant. We'll consider the constant current assumption. Both capacitors are very large. Again, the capacitors are also very large, and the voltage across them is constant. So these are the some assumption we consider for the deriving the Chuk converter equations. So again, we will just start with the switch on and switch off of the Chuk converter. So when switch is on, so here switch is on, you can see. So at that time, what is happening? So we have considered the constant inductor current now. So the inductor current is flowing in this direction. Okay. So also, so this inductor is also there. So this also has to flow from somewhere because this also has the current. So this current is flowing in this direction. Okay. And when switch is open, that time this reverse get shorted and the inductor current is flowing in this direction. And this inductor current again flows in this direction. Just one correction. I said there is no change in the polarity. Actually, here also we'll get the change in the polarity. Sorry for that. Uh, my mistake. So here also the polarity gets changed. Only what is happening, you can see the currents. So first, the IS current you can see. Okay, IS current. What is happening at the when switch is on, that time it is flowing through the this, and when switch is off, it is flowing through the this. Means it is a continuous. There is no interruption in the input current. Similarly, for the output current, the is inductor is supplying the output current in this position as well as this position. So there is no interruption in the current to the input as well as the output through the inductor. So that is the thing. So we are getting the filtering at the input as well as the output. Now for this, the average voltage across C1 is compared from the Kirchhoff's voltage law around the outermost loop. So if we apply the outermost loop, so this is the outermost loop, we can say. So the VC1 is equal to this voltage, VC1 voltage. So this outermost loop, we will apply this one, which is nothing but, sorry, outermost loop is applied this one. So this is the Vs minus VO. We have considered the constant current here. So there is no change in the current. So there is no DIL by dt. Okay. So there is no DIL by dt. Change is not there. So the voltage across this inductor is not there. So there is a short circuit of the inductor, this and this. And if we apply the outermost loop, so I will just erase it so that you will understand. Okay. So if I apply the Kirchhoff's voltage law for the this outer loop, total outer loop. Okay. So what are the voltages present? Vs is present. Actually, in practical here, this VIL1 also present. Sorry, VL1 and VL2 also present, and the output voltage also present. But as we have considered the constant inductor current here, here and here, if the current is constant, means there is no DIL by dt. So no DIL by dt, there is no change in the inductor current. So change in inductor current is 0. So you can say VL is equal to, which is equal to L di by dt, L DIL by dt, so which is equal to 0. So this is the short circuit. So these are these short circuited. So we can say VC1 is equal to Vs minus VO. Why we are doing that, we will come to in next some points. Now switch is closed, the diode is off, and the current in the capacitor C1 is, so this current is flowing through the capacitor. So this minus IL2 is flowing through the closed switch to the capacitor. With switch is open, the current in L1 and L2 force the diode on. So this diode is getting on here. Okay. And in that case, if you see the IC1 current, so that is nothing but the IL1 current. This current is flowing through this one. So this is the IL1 current. Now the power absorbed by the load is equal to the power supplied by the source. So here again we are saying that there is no uh, losses. Whatever input is there, input power is there, output power equals to. Now output is nothing but VO into IO. Minus VO because polarity are getting changed. So minus VO into IO, and IO is nothing but IL, because see, the same current is in this condition as well as this condition. The same IL is flowing through this one. And similarly for the input, so this is the one path and this is the second path. So the whatever IL is there, that is the equals to the IS. So that's why I have taken minus VO into IL2 equals to VS into IL1. For periodic operation, the average capacitor current is 0. So with the switch on for time dt and off for 1 minus dt, average capacitor current we can say it will be 0. So minus IL by dt, IL into dt, and IL1 1 minus d into t, which is equal to 0. So you can say IL1 by IL2 is equal to d divided by 1 minus t. Okay. Now again considering PS is equal to PO, VS IL1 minus VO IL, IL1 by IL2. This equation if I consider, so it will give us the minus VO by VS. So this term I can replace by minus VO by VS. So if I replace it and put in this equation, I will get the output voltage as the VO is equal to minus VS into D divided by 1 minus D, which is the same as the buck boost converter. But the advantages is that we are getting the filtering at the input as well as the output as compared to the buck boost converter. Here also the negative sign indicates the polarity reversal between the output and input. Right? So there are some again assumption made. The components of the output L2, C2, R are the same configuration as the buck converter, and that the inductor current has the same forms for the buck converter. Therefore, the ripple of the variation of the output voltage is the same. So at the output side, it is a buck converter, which I already shown. So that equation, whatever the ripple for the buck converter was there, so directly we can use here. You can derive it, you will get the same equation. Then the ripple in the C1 can be estimated by computing the change in the VC1 in the interval of when the switch is open, and IL1 and IC1 are the same. Assuming the current L1 to the constant at the level IL1, we have the same thing can be derived by this equation. And the fluctuation of the inductor currents are considered again same as the voltage across L1 switch is closed. So you can close the switch and write the equation, what is the Vs, and from that you can calculate the delta IL1. Similarly, delta IL2 for the inductor 2. Then from that, again here, the minimum size inductor current you can calculate by equating the IL we already know. So from IL and delta max min we can calculate, and from this we can calculate this equation. I will send this whole slides to you so that you will get the all the derivation for this one, because everything deriving here is not possible in this short time. So I will just give the overview, and then we will go in details. You can derive the equation. Okay, so that's all the some basic converter topology which I wanted to deliver here. Buck boost, buck boost, and choke converters. With that, I think we will stop here for today, and we will start tomorrow. There we will try to cover the some of the practical aspects which we are using in the all this converter, and as some student asked for the what other types of the converters are there which are used in the EV application. So I will try to cover that part. Is it okay?
Okay, sir.
Yeah. Of course, in this lecture, everything is not possible to cover and everything is not possible to explain also. I will trying to have the brief only of the all the some of the converters, and uh, of course some it is possible that some will get the here itself the working of the this converter, some will not get, but you have to go back and try to derive or the analyze the converter so that you can understand. If you don't understand, you can come tomorrow, ask me whatever doubt you have. I will try to solve it.
Sir, what are the advantages of co-converter over the buck converter?
Actually, this cook converter is the buck boost converter. Okay, it's not the buck or the boost. So it's boost converter. But if you consider the boost converter, our boost normal boost converter. So this is the boost converter, buck boost converter. Sorry. So here you can see what is happening. Inductor is present here. Okay, and in terms of the input current. Now, don't consider the working of the converter, only just consider the how the input current is going, this current. Okay, we have the source and from that source we have the input current. When switch is closed, the input current is flowing through this, right? So some current is flowing this IS is flowing this one, which is equal to the IL. Now when switch is open, there is no current flowing from the source. So the IS, if we draw the IS, so this is becoming 0 when the switch is open. Sorry, this is the 0, okay, 0. Again, when switch is closed, you will get the this current. When switch is off again, you will get the 0 current. Okay, so this is the IS. You can see it is not a constant or the smooth current. You are getting a very high ramp, then instantly you are going to the 0. So you are not, if it is a battery and you are trying to take the high current and again if you are stopping, then what will happen? It will affect on the life of the battery. Okay, interruptly you are taking the high current and interruptly you are stopping the current. So like that, if you are trying to do the continuously, so it will affect the life of the battery. If it is the battery is there, so it will affect the life of the battery. So that is not acceptable, like if the source is the battery. Okay, similarly for the load here, for the load, of course here the capacitor is supplying the continuous current, but for the inductor, when this switch is closed, so that time the inductor current is not flowing through this one, only this capacitor current is flowing, and when switch is open, that time only inductor current is flowing in this direction. So this inductor, whatever inductor filtering is there, inductor will try to oppose the change in current, so that is not getting applied to the load. So the capacitor only applying the or the keeping the constant current here, so not the inductor. Okay, so that is the issue when we consider the normal buck boost converter. So with this, if we go now to the choke converter, what is happening here? Again we will consider the IS. Only IS. Okay, when switch is closed, this switch is closed, this current is flowing in this direction, so rising current is flowing, and when switch is open, so this current, still current is flowing in this direction actually. Okay, means there is no interruption. So there will be the decaying in the current, but no change in the interrupt change. So like that you are getting. And this we can control ripple by increasing the inductance. So if I increase the inductance, there will be the very small rise or the fall. Only this much ripple you are getting. So you are not affecting the life of the battery here. Okay. Similarly, for the load, you can see when switch is closed, so the inductor current is flowing in this direction. So the inductor current is flowing. And when switch is open, again the inductor current is flowing in this. So inductor is trying to filter the output current, not only capacitor. So the capacitor requirement will get reduces as the inductor is filtering the current here. So what we can conclude that it is having the filtering in the input source, input as well as the output. And there is no abrupt change in the input current in this converter. So that advantages we are getting for the Chook converter.
So, sir, it can be able to use in a state of charging and discharging in batteries.
Yes. Not state of charging and discharging of the battery, because it is a not bidirectional. Uh, so you can, sorry. Here the power will flow always from this side to this side. No power is flowing from the this side to this side. So it cannot be bidirectional. So for the charging and discharging, we require the bidirectional converters. I will take the one example of the buck converter, which can operate as a charging and discharging in both the direction. There is a converter, the modification of the Chook converter, which will gives the both direction power flow. So that converter is also there, but we will take the example of the buck converter, which can be used to charge or discharge the battery. Okay.
Okay, sir. Thank you.
Because if we consider the battery, okay, so charging of battery means power has to come from this to this side. Okay. And discharging of battery means power has to go from this to this side. Both direction power flow has to be there, not the unidirectional. Then only charging and discharging is possible, right?
If we can place that resistor or battery in between the couple C1 and IL2, then
Then you are not, see this C1, C2, L2, L1 are the storage element. But if you are not taking any power from this or this in this operation actually, so whatever charging is there, that much discharging means when on is there. So if you are in on time, if you are charging this inductor, in off time you are discharging that inductor, means whatever energy is charged, that much energy you are taking. So over the cycle, charge and discharge is equal to zero. Means they are acting as a only a they are not supplying any power. So they are getting storing the energy and releasing the energy. Whatever stored energy is there, that much energy they are storing. They are the passive elements. They are not elements. So the operation point of view, there is no charging or discharging happening in the means over the cycle if we consider. So there is no charge or discharge of the that inductor or capacitor. So if we replace this with the battery, so then also what will happen, for the on time you are charging the battery and off time you are discharging the battery. You are not continuously charging or discharging the battery. So you are not taking any power from the battery, or you are not giving power to the battery. So we cannot replace that capacitor by the battery, or it will not be useful. See, Discharging
Okay, sir.
means
Thank
what?
you.
Whatever energy in the battery is there, that we have to give to the load. Okay, means we continuously taking the power and sending it to the load. So that is the discharging. Okay. Charging means what? Continuously we are feeding the power to the this battery so that it will start the charging. But whatever this capacitor and inductors are there, it is not the like that operating. For the on time they are storing the energy, and off time they are releasing the energy. Continuously they are not either storing the energy or they releasing the energy. So if the battery is considered here, so it will over the cycle, so there will not be change in the charge. For on time it will charge, and for off time it will discharge, and after the time you will get the same charge which was there at the initial stage. So there is no increase in the charge or the decrease in the charge. So how you are saying that you are taking the power from the battery, right?
You are right, sir.
Okay, so that's all for today's lecture. So I will try to some of the practical aspects in the tomorrow's lecture, and whatever doubts you have, and one homework which we have given, so that we will try to solve in the tomorrow's lecture. Is it okay?
Okay,
In
sir.
if you want to
Yes.
anything else, if you want
Okay,
to
sir.
have for tomorrow's lecture, just let me know today itself so that I can prepare it. Now itself you can just tell me if you want to know anything else for that.
Okay. All students are encouraged to come up with some doubts as well as some uh, their queries so that those queries can be resolved in the tomorrow's lecture. So thank you very much, sir, for uh, making this very easy for the students. I mean, they need to practice this, as you mentioned, rather going just remembering the equations. They need to analyze, and it will be easy for them if they can understand the working of converters, so that they can derive on the spot the expressions of the parameters, what are the expected for calculating LC values. Okay, so thank you very much for today's session. We will join for your session tomorrow.
Yeah, thank you. Thank you. Good night. Good night,
Good night.
everyone.
Thank you, sir.